Okay, I was hoping to record without the tabs at the top, but it actually causes the recording to stop. So here we go. What we talked about yesterday was a little deeper about this concept of friction. And the issue with the frictional force, can I move this? So the issue with friction is that we're trying to understand what causes the source of it, and it turns out that because of the source of friction, it actually affects it so that we get more than one kind of friction. And so really important to kind of understand the source of friction because otherwise it doesn't really make sense. Like, why do we have two kinds of friction? So the friction comes from the irregularities of the surface, the irregularities in the surface, even though surfaces might seem very smooth. If you could shrink yourself down to the atomic level, you would definitely see that it's not perfectly smooth. I mean, even if the atoms were all lined up perfectly, they're round. They're not like little squares put together. So even then, you'd still be following like the little hills and valleys of the actual atoms themselves. But it turns out that atoms don't combine together in long straight lines like that for very long. So those surfaces, even though they might seem smooth, like glass, um, it's not. It is not smooth at all. It is actually very irregular. Now, it's smoother than other surfaces, but it's certainly not smooth by any stretch of the imagination. So those irregularities, they kind of overlap each other, and in order to move sideways, the two surfaces have to kind of move away from each other, and they will. As you push them, they will start to slide upward as they try to slide sideways until eventually they get free, and then they'll be able to slide. And so that's one of the reasons why when you go to sliding friction, the force drops because they're no longer, partially interlocked. The second thing is this amazing, unbelievable thing about the universe that everything you can see, I mean everything that you can see except for light, all of the table, chairs, your body, the air, the water, the food that you eat, everything is made up of only three particles: the proton, the neutron, and the electron. Now, we're not going to talk about the neutron too much right now because that guy doesn't participate. He has no charge, so he doesn't participate in the electric force. But the proton and the electron are very strongly charged. But nature conspires to prevent us from seeing how much charge there is. Your room is filled with trillions, but it's not, to say trillions is an underestimate. It's ridiculous the number of charges that are in your room right now with you. In your body alone, the number of charges is incredible, and that's all your body is made up. It's made up of electrons, protons, and neutrons. That's it. But you don't notice their effect because they combine together to neutralize themselves outside of the atom. But inside the atom, oh, you'll definitely feel the electric field. You'll feel the electric force if you could dive into an atom. You can make yourself really tiny, make yourself maybe like 1/100th of the size of an atom, and you jumped into an atom. As you enter the atom, you say, oh, very negative. So it's very negative because you're with the electrons, and you're in the area of the atom where it's very negative. But as you approach the center, it's going to transition to becoming more positive because you're approaching the nucleus where all those positive charges are at. So inside the atom, you feel the electric force, but then you get outside the atom and you say, I don't feel anything. I don't feel any electric force because it's canceled out in the atom. Now, when the atoms bond, they don't bond just straight up in a line. They will form angles and there'll be a little geometry to them. Also, the electrons inside of the atom will kind of move around a little bit to different positions depending on how they bonded. And that causes what I would refer to as a little asymmetry, meaning that even though it's neutral, there are areas along the surface where it feels more positive and some places feel a little more negative. And those two things draw each other together. So those opposing charges tend to want to draw the two closer together, but only where they touch. Now, the mistake is to think that when you put a block of wood on a table, that all of the block of wood is touching the table. It is not. It is a tiny, tiny, tiny little percentage of that block is actually physically touching the atoms of the table. It's very difficult to do. Only in a few selected spots, like right there, or right here might be close enough, or right there, that's where the electric force is happening. Now, when the two surfaces begin to slide, they're going to slightly move away from each other because the overlap won't allow them to slide. So if you don't allow them to move away from each other, they won't slide. As they move away from each other, the electric force gets weaker. And because the electric force gets weaker, that's going to mean that the sliding friction will be significantly less because both the irregularities don't overlap and now you've moved farther away and those both reduce the value of the frictional force. So this is why we have two kinds of friction. We have static and we have kinetic. The static friction is the friction that you have to overcome to start something moving, and the kinetic friction is the friction you feel when something is already sliding. Now, interesting fact, static friction is always more than kinetic friction. And I know you know this. I'm sure you know this. Think about something that you pushed that was really heavy, or you were trying to move it, and it did eventually slide. You pushed on it, it didn't move, so you pushed a little harder. You continued pushing harder and harder until eventually it did start to move. But when it started to move, didn't you feel it give way? Didn't you feel it like it felt like it was accelerating, even though you were just barely over the force to get it moving? And so let me just give you a quick explanation. Let's say that the thing that you need to move is 100 newtons. Okay, you start pushing on it with 20, it doesn't move. You push with 50, it doesn't move. You push with 90, still not moving. You push with 100, it's still not moving because you're right at the threshold. You're at the limit for static friction. Any more and it will start to move. But as soon as I go to 101, you might think like, oh, imbalance. It's 100 one way and it's 101 the other way, so I got 1 extra newton going this way. But no, that's not actually what happens. What happens is that when you hit 101, the static force disappears. It just disappears like that and transitions over to the sliding friction. So it goes from being 100, right? So we're at 101, you're pushing. The static friction is now gone. You drop to the lower friction. Now suddenly you've got 30, 40, 50, 60 extra newtons. So it begins to accelerate quickly. And as long as you keep it moving, it won't go back to the static friction. But the moment you stop, I mean, just test this out. Please test this out. Later today in the evening, find something that's fairly heavy. And I am sure you will notice that it takes more force for you to start it moving than it takes for you to keep it moving. Once you get it moving, you've transitioned to kinetic friction and it will be easier to move. So therefore you want to keep it moving until you get it to the spot you want. Because once it stops, you're going to have to go back to the other one. You're going to have to push a little bit harder to make that thing move. Now, the most interesting thing that I can think of that we can talk about with regard to static and kinetic friction is the way it affects car tires. So what I'm going to show you is, we talked about yesterday, even though when the car tire is rolling, it might seem like, oh, that's definitely kinetic, because that's what kinetic means. Kinetic means motion. But the important thing is, what are the surfaces doing? Are the surfaces sliding, or are they rolling means no sliding? So I know this is like a really abstract thing. It's like kind of hard for people to visualize sometimes. But when the tire is rolling, that's static friction because the two surfaces are not sliding against each other. Yes, the wheel will roll away, like I get it. It's not like the wheel is stopped, but the two surfaces are not moving relative to each other. Therefore, that is static friction, and that is what you want. Because the static friction is going to give you the most acceleration that you can get because, of course, it's more force. If the static friction will give you 100 newtons, that means you can propel yourself with 100 newtons. But if you're with kinetic friction, that means you can only propel yourself with 70 newtons. So it's not going to be as much. So you're not going to accelerate as fast. You're not going to pick up speed nearly as quickly. So there's two aspects to this. One is speeding up and the other one is slowing down. Let's just deal with the speeding up, and then next week I'll come back to this and we'll talk again, and I'll show you the braking side of it. I'm going to show you a video right now, so let me do one thing here. Let me stop this. Let me present to you drag racing. It's going to be awesome. Old school versus new school drag racing. Oh, I'm sorry. Give me 1 second, guys. Stupid monitor stops working. It's very frustrating because I can't see you guys except for on my other monitor, which stops working every once in a while. Can somebody just tell me, just turn your mic? You can see the video now, right?
No, we cannot.
No, you cannot. All right, interesting. Why is it not? Oh, I see. Haha. How about now? Yay, I figured
Yes,
it out.
sir.
Okay, apologize for that. All right, so I have the volume turned down. I think I have the speed turned down. Hold on. Oh, no, I don't. You know what? I'm so sorry. Just give me a second here. I'm trying to get this. It says normal. That's interesting. Let's drop down the quality just a bit so it'll play faster. All right, here we go. Two things I want you to pay attention to. Before the race, notice they spin their wheels. And when they start the race, notice that they do not spin their wheels. So I know it was a little difficult to see because we're kind of we missed a little bit of the first part here. But notice that you did not see any smoke come off the tires on that car. Okay, when you see smoke coming from the tires, that's kinetic friction. That's the tires are sliding. When you don't see smoke, that's the static friction. So those speeds were, I think it was 130 miles per hour that they just went. Okay, so you see them now, they are spinning the wheels. So that might make you think like, well, why are they spinning the wheels? They're trying to warm the tires up. You know that. Rub your hands together. You know that rubbing things together makes them warm up. And warm tires have better grip than cold tires. Now watch what happens. Pay attention to the back wheel. That's the drive wheel. Did you see any smoke come up at all? Did you even see the slightest bit of smoke? No. You did not see anything come off that tire because these drivers are so good that they can push the accelerator just to the edge where they're about to start spinning the wheels. And that's the trick. That's the trick to drag racing. It's not just who has the most powerful car. The guy was going 142 miles an hour. It's not just who has the fastest car. It's who can get that accelerator to just that, right to that threshold. Let's say that your threshold is 7,500 newtons. You want to go with 7499 because if you go over 7,500, the tires are going to start to spin and you lost the race. You instantly lost the race right there because you dropped your propulsion force. When the friction went away to the lower level, you dropped your propulsion by 30, 40, 50%. And of course, how are you going to beat a car if you give away 50% of your power? Look at the cars spinning their wheels. They're just trying to warm up the tires. Now watch these cars. Look for even a hint of smoke coming from those back tires. This is the last one we'll look at. Oh my God, how slowly can they drive up to that starting line? By the way, I think that might actually be my car. I think that is a Chevy Nova. I'm not sure. The one in the front ground. Oh my God, start the race. I mean, you tell me. I'll post this video so that you guys can go and back and look at it. Show me any smoke coming off. That's what makes drag racers drag racers. They can accelerate the car without spinning the wheels. Even though it might look cool, that means you're going to lose the race. So they don't spin it at all. It's so difficult to do. I just can't tell you how difficult that is for drivers to do. All right, let me stop presenting and let's go on to the new material. There we go. All right. So remember, I'm recording this. So if you don't want to take notes and just listen and then just go back and record it from the video, and you don't even have to listen to the video, then you just copy the notes, that's fine. This is really more for people who are getting at level 3 and level 4. So if you're level 1, maybe you just want to listen right now. And if you get to level 3, then you'll go back and watch this video because I'm watching it right now. I can see that it's recording. This thing called the coefficient of friction. Okay. Let me ask you, well, it's too late. I can't even ask you. I'm sorry. I was going to ask you what a ratio is, but I feel like it's partially revealed by what I'm writing. I think it would be very worthwhile for us to think about what it means to be a ratio, because that's like a mathematical term that it comes up a lot. And I've seen people in this class and in other classes who have used ratios. So obviously I know some people do understand a little bit what ratios are. If you say something is 2 to 1, that is a ratio. Technically, I agree, that is a ratio. You say 2:1. But I wouldn't think about ratios like that. I would think about ratios like a fraction. A ratio is a fraction. It's what fraction of this thing is this other thing. So for example, if I think about my kid's allowance, I give like certain money for their allowance, not very much money, but a little bit for the work that they do. One child gets half of it, the other child gets half of it. So that ratio is 50%. Each child gets 50% of the total pool of money that's available in their allowance. So a ratio is a fraction. Okay, now because it is a fraction, that means that basically it's almost the same thing as a percentage, because that's what a percentage is. So if, for example, you said the ratio was 0.5, so 1 divided by 2, that's 50%. If you said the ratio was 0.7, that's 7 over 10, or 70%. So a ratio is how one thing compares to another, but done in the form of a fraction. Okay? So the coefficient of friction is the ratio of the frictional force to the normal force. The ratio of the frictional force to the normal force. These are the two forces that surfaces exert. So when I push against a surface, let me use my phone as an example here. When I push against my phone, when I push against the phone, there's a normal force. It pushes back against me in the opposite direction. When I slide my hand along my phone, I get a sideways force. It's not perpendicular, it's parallel to the surface. That's the frictional force. And that's it. Those are the only two forces that can be exerted by a surface, is the frictional force and the normal force. So the coefficient of friction says, let's look at the ratio of those, and that helps us to understand whether it's going to be easy for things to slide or hard for things to slide. So for example, if the coefficient of friction is 0.1, that would be like if you walked on ice. Very slippery, not a lot of friction. So the coefficient of friction for ice might be like 0.1. And what that means is that of the normal force, which is, in this situation, basically your weight, the gravity of the earth pulls you down, the floor pushes up, the two are in balance, so the normal force that you feel is just going to be equal to your weight. So what the coefficient of friction says is what percentage of that will get turned into a sideways frictional force. So if the coefficient of friction is 0.1, like it would be probably for ice, then that means 10% of the normal force. So if you have a weight of 500 newtons, that means you'll get 50 newtons of frictional force. Not very much. That's not a lot of force to propel yourself forward. But if you are walking on concrete, where the coefficient of friction between your shoes and the concrete is maybe like 0.8, that means you'll get 80% of your weight turned into a sideways force. So the coefficient of friction is just simply showing you how much of your normal force is going to get turned into a sideways frictional force. And obviously, the more sideways frictional force we have, the more we can propel ourselves forward. Right? So this is where the coefficient of friction is like a really important aspect for you to understand. Now the symbol for it is the Greek letter mu, and I've actually written it 3 times. So this is what it looks like when it's typed. It usually has a straight line on the left, but look, the way you make that symbol is like this. You write the letter U, and then you go to the left side of it and you just draw a line down it. Or you don't have to do it that way, you could do it this way also. Okay, but it should look like the letter U with a long tail coming off the left side of it. It can go straight down or to the left. It's the Greek letter M, it's pronounced mu, and it is the letter that we use to represent the coefficient of friction. I don't know why, it's a mystery to me. I really don't know why we chose that letter. But I do know there are not enough letters in the English alphabet to accommodate all of the properties that exist in the universe. So, sometimes we have to reuse letters and sometimes we just use other letters. I don't know why. For some reason, the coefficient of friction is the Greek letter mu. So you may be given the frictional force and the normal force and be asked, what's the coefficient of friction between these two surfaces? And then you just divide the frictional force by the normal force. It's not too tough to do. But the way we'll probably use the equation more often is like this. So all I did was solve for the frictional force. And that required me to multiply by f of n, which moved the f of n up to this side over here. So here is an actual equation for a force, and there's not very many equations like this. We have an equation for weight, and then that's it. We don't have any other equations for force other than the generic equation, ma, but no specific equations that allow you to calculate a specific force. Only a few of them have that. Friction has it, weight has it. Most of the others don't really have a formula like that I could teach you. So if I told you, hey, the coefficient of friction for this kid running on a track is 0.75, and this kid weighs 500 newtons, you should recognize that the kid's weight is going to be their normal force. That's going to be the same as the normal force, and that you can then calculate the frictional force. Now, why do you want to calculate the frictional force? Because you want to know how fast the kid's going to accelerate. And the kid is going to use the frictional force. When they push against the ground, they're only going to get as much force as the friction can return. So when they push against the ground, they'll only get as much return back to them as is available through the friction. This is why it's really important that the coefficient of friction be very high if you want to be able to try to accelerate quickly. Because when the coefficient of friction is very low, you're not going to get very much frictional force, therefore you're not going to accelerate very rapidly. Now, to just complete the whole picture, remember there's 2 kinds of frictional force. So that's where we come to the static and kinetic again. So each of those has the same formula. It's the frictional force is equal to mu times f of n. But I just want to really emphasize this one point. The static friction is a little weird because the frictional force is a reactive force. When I push against my hand, it doesn't slide. I push a little harder, still not sliding. I push hard, and now it slides. Okay? So when you first push on something, you push lower than the static force, it's not going to move. So you push a little harder, it still doesn't move. The static friction will resist you. It's not like it's alive. It's not like a person. It's not like saying, I'm going to do whatever that other person says, I'm going to do the opposite. But it is a reactive force. As you push harder on something that's very heavy and won't slide very easily, you will notice that as you push harder and harder, nothing's happening. And then when you stop pushing, that force goes away. But the important thing is, what's the limit? And that we would call the threshold. So what's the threshold? Because when I know what the threshold is, I know how much force I need to apply in order to make it move. So if I go below that threshold value, it's not going to move. It's just going to sit there. As soon as I hit that threshold value and go past it, now we switch over from this guy to this guy. Now we go to kinetic friction, and the friction gets much lower. So for kinetic friction, it's just F of F equals mu times F of M. Okay, but technically speaking, for the static friction, it's less than or equal to the coefficient of friction times the normal force. Now, for our purposes, you don't need to write it like this, even though that's technically correct. I am perfectly happy if you just say equals, because most of the time we're only going to be concerned with what was the maximum static force, because that's the force I have to overcome in order to make this object move. So we'll use both the equations like this, but I just wanted to clarify it for you because when you look at this in the book, which by the way, it's in chapter 5, this is the only thing that is in chapter 5 that we're looking at right now. Everything else is in chapter 4. It's just one little detail in chapter 5 that I want to add to this unit, and that is this idea of the coefficient of friction. Very important idea to understand, and especially important to understand the difference between static and kinetic friction. And the reason why I'm telling you that is because it's so relevant to driving. It's so relevant to driving to not spin those, do not let the wheel slide. That is never good. I mean, if it's fun, I mean, I'll say it's fun, but it's never good. Next week we'll talk about the braking, and I'll come back to this again, and we'll just go over it again one more time. We'll just re-emphasize it one more time, and I'm sure that every one of you can understand this. If you just go and look at that chapter 5, it's only maybe 3 pages or 4 pages, and just reread through it, and I'll bet you now that you've heard it, when you read that, it's going to make more sense to you. Like, you'll understand what they're saying. It'll make sense. But you don't need to worry about it until you get to level 3, because you won't see this at level 1 or level 2.